Welcome to today's Explainer. Have you ever looked up at one of those modern highway flyovers and just wondered, how are those concrete girders so impossibly thin? Compared to those old, super bulky bridges we used to build, they almost look fragile, right? Well, you're definitely not alone in wondering that. Actually, in Professor Arvind Deshmukh's engineering class, a student named Priya noticed this exact same thing. And her observation perfectly sets the stage for what we're getting into today, the absolute magic of post-tension segmental construction. Or, to keep it simple, pre-stressed concrete. Today, we're going to explore the mathematical heart and the brilliant logic behind how engineers use pre-stress to make sure concrete never faces its ultimate enemy, tension. Okay, let's dive right into this. If you recall the basic philosophy from last time, we basically want to put concrete into constant compression. We want to squeeze it so it never has to deal with tension, because tension is exactly what causes it to crack and fail. But, engineering isn't just about philosophy, right? It's about precision. So the core mysteries we really need to unravel today are, well, exactly how much of this pre-stressing force do we actually need? And perhaps a bit more terrifyingly, what happens if that carefully applied force just leaks away over the next 30 years? Well, to answer that, we've got to start with the fundamental rules of how forces interact. To make sense of these forces, we rely on this golden rule in structural analysis called the principle of superposition. It sounds fancy, but it basically just states that the final stress at any point in a beam is the algebraic sum of the stress from the pre-stress plus the stress from the external loads. Professor Deshmukh actually uses this brilliant analogy for this. Think of it exactly like a bank account. So you deposit this massive amount of compression into the beam. That's your fixed deposit, right? That's your pre-stress. Later on, external loads, like heavy traffic or just the bridge's own weight, they come along and try to withdraw tension from the bottom of the beam. Now, as long as your initial fixed deposit of compression is larger than that tension withdrawal, your account never goes into the negative. The beam literally never goes into tension. Let's try to visualize this for a second. Imagine a totally plain concrete beam just sitting there on two supports. In stage 1, we apply a pre-stressing force right smack in the center. The whole beam gets squeezed uniformly, so everything is in nice, safe compression. But then, in stage 2, we apply external loads, like actual vehicle traffic. This load forces the beam to bend downward. And this downward bending, that is the villain of our story. It stretches the bottom fiber of the concrete apart, which creates that dreaded tension, while at the same time adding extra compression to the top. Now, this brings up a really tricky question. Think about it. If we put our pre-stressing steel right at the center of the beam, the whole thing compresses uniformly, right? But when that heavy traffic rolls over it, the bottom of the beam is going to need way, way more compression than the top just to fight off that bending tension. So what do clever engineers do? Do they just keep stuffing more and more steel into the center? No way. They change the game entirely through a concept called eccentricity. It's a real game changer. What happens if we take that steel and place it lower, closer to the bottom fiber, instead of right at the center? Let's grab a mental wooden ruler to picture this. If you press down on the top of a ruler with one finger right at the center, it bends down, right? The top compresses, the bottom stretches. Pretty simple. But now imagine applying a massive, squeezing force specifically at the bottom edge of that ruler. What happens then? Well, first, the whole ruler gets squeezed. But because you're pushing off-center, down at the bottom, it actually forces the ruler to curve upwards. This is absolutely brilliant. We're using the pre-stress to create an upward bending moment. We are essentially pre-bending the beam upwards so that when those heavy downward loads eventually arrive, they just flatten the beam back out instead of breaking it in half. So, how does all this build into the final mathematical condition of the beam? Look, textbooks are going to throw complex formulas at you, full of P over A and moments over section modulus. But really, you just need to conceptualize it in 3 simple actions. Step 1, squeeze. The direct force compresses the entire beam. Step 2, bend up. Because the steel is placed low down, it creates an eccentric pre-stress that literally arcs the beam upwards. And finally, step 3, bend down. The external loads of the real world push it right back down. So it's just squeeze plus bend up plus bend down. And that equals your final stress. Now, here is where a lot of students and novice engineers kind of get tripped up. A pre-stressed concrete beam actually lives 2 completely distinct lives, and it faces totally different dangers in each one, so we have to check its survival at 2 critical stages. First up is the transfer stage. Think of this as the birth of the beam in the factory. The concrete is young, it's green, maybe it's only at like 70% of its final strength. At this point, the only forces are that massive pre-stress and the beam's own weight. There's no traffic on it yet. Then, the second life is the service stage.
This is its working life out in the real world. By now, the concrete is fully mature and strong, but it has to carry the maximum possible loads of traffic and gravity.
Now, what's really interesting about this slide, and when you look closely at these original source notes, is that because the conditions are so different, the dangers are actually reversed. At the transfer stage, because we have that huge eccentric force bending the young beam upwards, and remember, there's no heavy traffic pushing it back down yet, the real danger is actually at the top of the beam. The top fiber might stretch and crack in tension, or the bottom might just crush under all that intense compression. The Indian code IS 1343 actually sets really strict limits just to make sure the young beam survives this pretty violent birth. All right, let's lock this into our mental notebooks really quick. At the transfer stage, the loads are just pre-stress and self-weight. The critical danger zone? The top fiber. Why? Because it might crack in tension from that upward bending, and the concrete is still young and vulnerable. Now, contrast that with the service stage. Here, we add the live load, so the critical danger zone completely flips to the bottom fiber, which is now trying its hardest to stretch and crack from the massive downward bending of those full loads. The concrete is mature, sure, but the external forces are at their absolute peak. If engineers only had to worry about day 1 and year 1, well, the job would be pretty easy. But now we have to introduce the dramatic conflict that literally keeps structural engineers awake at night. We're talking about the invisible pre-stress leak. See, when you pull steel cables with hydraulic jacks to an immense tension, say 1,800 newtons per square millimeter, and you lock them in place, you desperately want that force to just stay there forever. But unfortunately, nature has other plans. Over time, that carefully applied pre-stressing force just drops. This leakage actually happens in 2 distinct phases. First, we've got immediate losses. The second you release the hydraulic jack, the steel tries to snap back, which instantly squeezes and slightly shortens the concrete. That's elastic shortening. Also, the wedges holding the steel might slip a tiny bit, just a few millimeters, into the anchor, but the real slow-motion thieves here are the time-dependent losses. As concrete dries over the years, it shrinks. Plus, under constant, heavy squeezing, concrete experiences something called creep. Just picture placing a heavy textbook on a foam mattress. Over a few months, the mattress just keeps compressing slowly. And finally, the steel itself gets tired. Much like an old rubber band losing its snap over the years, the steel relaxes and loses its internal stress. So how much force do all these invisible leaks actually steal? Get this, a staggering 15 to 30% of the initial force is lost over the lifespan of the beam. That is wild. And this is the true challenge of the structural engineer. You aren't just designing for ribbon-cutting day when the bridge opens. You literally have to predict the future. You have to design a beam that's still going to hold together 30, 40, or 50 years from now, even after it's lost nearly a third of its internal strength. To really appreciate this magic, we need to see it in action. Let's imagine a simple rectangular beam. We apply a massive pre-stressing force of 1,800 kilonewtons, and we place it eccentrically, 150 millimeters below the center. At the transfer stage, again, the birth of the beam, we only care about this force and the beam's own weight. After crunching the numbers for the direct squeeze and the bending forces, the top fiber ends up at a gentle 3.33 newtons per square millimeter of compression, and the bottom is squeezed tight at 16.67. The young beam is perfectly safe. It is 100% in compression, absolutely no tension anywhere. But now let's fast forward to the service stage. The bridge is fully open. Now we have to add a massive live load moment of 300 kilonewton meters. Basically, picture heavy trucks driving right over our beam. This new downward load is directly fighting our carefully designed upward pre-stress bend. So we use the exact same logic, but we add that new bending stress caused by the heavy traffic. And then we recalculate those top and bottom fibers. And brilliantly, when you run the numbers for the bottom fiber, which remember is facing the maximum stretching force from the traffic, the direct compression plus the eccentric upward bend minus the downward bend from the loads, it equals exactly 0. 0 newtons per square millimeter. This right here is what engineers call a zero tension condition. It's just this elegant, perfect balance. The bottom fiber has absolutely zero tension ripping it apart and zero compression crushing it. It is perfectly neutral under maximum load. But here is the crucial point. This kind of perfection, it doesn't happen by accident. As Professor Deshmukh notes, in major design offices across India, places like L&T, Afcons, or the railway design offices,
Engineers don't just plug a few numbers into a single formula and call it a day. No, they design iteratively. They assume a pre-stress force, they assume an eccentricity, they check the stresses at transfer, they check the service loads, they calculate the future losses, and then they revise the whole shebang. It is quite literally a delicate dance between compression and tension, justifying that absolute perfect balance.
And all of this brilliantly illustrates exactly why predicting the future is the hardest part of the job. I want to leave you with this provocative thought from the professor's class. A student, Anjali, was asked, if a beam is designed to have a safe 2 units of compression at the bottom fiber when it opens, but it loses 25% of its pre-stress over 30 years, what happens? Anjali did the mental math. If the force drops by 25%, the upward bending that protects the beam also drops. That safe compression flips into negative 6.25 units of tension. So the answer is yes. After 30 years, the beam would suddenly crack under everyday traffic. We don't just design for today, we're designing for the invisible leaks of tomorrow. So the next time you drive over a seemingly impossible paper-thin concrete flyover, maybe ask yourself, what other invisible battles between physics and time are secretly holding our modern world together?